Hi guys, this is lesson 8.8. It's called Differences of Squares. Back in lesson 8.4, we talked about some specific patterns and we talked about the product of a sum and a difference. And today we are going to look at that from the other direction. Instead of multiplying the sum and the difference, we're going to factor it. And so this is the one that I told you about was a very important pattern, and it is extremely important to be able to recognize it, and we actually have to memorize it because we have to be able to recognize it. All right, when we see it and we need to factor it, it's going to look like this: a squared minus b squared. This term will be a perfect square, and this term will be a perfect square, and there will always be subtraction between in the middle. And when we factor this, it's going to make a really nice a plus b times a minus b. And if we do FOIL, we can see why that happens. A times a gives us the a squared. A times b gives us a negative ab. And b times a gives us a positive ab. And then b times negative b gives us our b squared. B times negative b gives us a negative b squared. So what happens is this outer and inner part cancels, and so we end up with a squared minus b squared, not a trinomial, but a binomial instead. So let me show you some examples. Example 1 looks like this: 16h squared minus 9a squared. And what I can recognize here is that 16 is a perfect square. 4 times 4 is 16. H squared is a perfect square. H times h is h squared. 9 is a perfect square. 3 times 3 is 9. And a squared is a perfect square. A times a is a squared. And we have a minus in between. So we call this a difference, that means subtraction, of two squares. And 16h squared and 9a squared are both squares, perfect squares. So here's how we're going to factor it. We just know that it's going to factor into this pattern: a plus b times a minus b. So I need to have the square root of 16h squared. So the square root of 16 is 4, because 4 times 4 is 16. And the square root of h squared is h, because h times h is h squared. We're going to have the plus, and then we need the square root of 9, which is 3, because 3 times 3 is 9. And the square root of a squared is a, because a times a is a squared. Then we're just going to actually write this 2 times, once with a plus and once with a minus. We can test this out. 4h times 4h is 16h squared. 4h times negative 3a is negative 12ah. And the reason that's not looking familiar is because this is positive 12ah, and together they cancel, so that we will have just two terms. 3a times negative 3a is negative 9a squared. All right, let's just work maybe another one here. 121 minus 4b squared. I know that 121, the square root of that is 11. 11 times 11 is 121. And I know the square root of 4 is 2. The square root of b squared is b. And I'm going to have one of each of these, 1 plus and 1 minus. And I can check that. 11 times 11 is 121, and 2b times negative 2b is 4b squared. The part that does the magic is this negative 22b and positive 22b cancel out. Okay. 27g to the third minus 3g. Okay, hopefully you're going, wait a minute, 27 is not a perfect square, and neither is 3. And neither is g to the third. But here's what's happening. We have common factors. If we have common factors, we need to factor them out. The first thing we want to do when we factor anything is actually factor out the common factors. So common factor here is 3. 3 goes into 27, and 3 also goes into 3. And then we also have a common g. So if I factor out 3g, what's left behind is 9g squared minus 1. Okay, I could use the distributive property to check myself. 3g times 9g squared is 27g to the third, and 3g times negative 1 is negative 3g. All right, so this is factored into this factor and this factor, but this factor is a difference of squares, so we can keep factoring. Okay, I'm going to keep the 3g. It's still part of my end answer, but I'm going to have 3g plus 1, because 9 is a perfect square, 3 times 3 is 9, g squared is a perfect square, g times g is g squared, and 1 is a perfect square because 1 times 1 is 1. And then I need to have a plus 1 and a minus 1. It doesn't matter which order you put those in. If I use FOIL, then I will notice that my outer and my inner cancel, and that I would have 9g squared minus 1. So I have 3 factors here. 1, 2, 3, and that is completely factored now. Okay, here's another example. This actually moves on to example 2, where we have something a little more than just factoring once. Okay, I have b to the fourth minus 16. Those are both perfect squares, so I know I'm going to factor into our 1 plus and 1 minus. The square root of b to the fourth is b squared, because b squared times b squared equals b to the fourth. And the square root of 16 is 4, because 4 times 4 equals 16. So I have b squared plus 4 and b squared minus 4. Now, I still have squares. Look, b squared is a perfect square, 4 is a perfect square, but only one of these has the subtraction. So we're going to keep b squared plus 4. It is not factorable because of that plus sign. There's nothing here that will factor and cancel out the middle term. So this is not a difference of squares. It's just 2 squares with a plus sign. So those are prime. You can only factor them with imaginary numbers, and we're not going to do that right now. So we can say that that expression is completely factored. However, b squared minus 4 can be factored into b plus 4 and b minus 4, because it does have the minus sign in it. And b times b is b squared, and 2 times 2 is 4. So now I have this factored into 3 factors. Yes, that's as much as I want to say about that right now. Okay, here is another example in the same set. 625 minus x to the fourth. All right, this is a perfect square minus a perfect square. I do have subtraction. 625 is, I believe it's 25 times 25. And we can test that out here. 25 times 25 is 625. So that's cool. We're going to have 25 there. We're going to have 1 plus and 1 minus. And then x squared times x squared equals x to the fourth. So here's x squared. All right. This first one is complete because it has a plus sign in it. The second one can be factored. So let's just hang on to this first one just the way it is. And the second one is going to factor some more because 25 is a perfect square and x squared is a perfect square. 5 times 5 is 25 and x times x is x squared. So we're going to have 5 plus x and 5 minus x. We can use FOIL to check ourselves, but this is completely factored. This one cannot go down any further, even though it has a perfect square and a perfect square. It has a plus sign. And then we have 5 plus x and 5 minus x. All right. Let's move on to example 3. What if we have 5x to the fifth minus 45x? Well, first of all, we have common factors. You want to look for common factors all the time. Common factor here is 5 and x. If I factor out 5x, I will get x to the fourth here minus 9. Okay, when I've factored, if I use FOIL to go back, I can check it. 5x times x to the fourth is 5x to the fifth, and 5x times negative 9 gives me negative 45x. All right, what I can see now is that this is a perfect square, and this is a perfect square, and this is a minus sign. So keep my 5x, and I'm going to convert that into two binomials. X to the fourth is x squared times x squared. You get used to these after you practice some. So I'm going to start with x squared, and then 9 is 3 times 3. So I'm going to have 1 plus and 1 minus, and I'm going to have a 3 here. All right, the x squareds make me think that I'm going to factor again like I did up here, but I'm not, because 3 can't be factored. I'd have to factor and use square root signs. So this is going to be complete just the way it is, like that. All right, let's do the next one. 7x to the third plus 21x squared minus 7x minus 21. So a little hint here is, well, just keep looking for common factors. And I can see that there is a lot of 7 happening all the way through this. So we're going to have a common 7. Let's get that out. If I factor out the 7, I'm going to have x to the third plus 3x squared minus x minus 3. Notice I didn't take out any x's because 21 doesn't have an x. All right, now I have a situation where I can maybe factor by grouping. I have 4 things, so I want to look at it like this and watch out for this negative x. It's kind of funny there. All right, let's see what we can do with the factoring by grouping. Leave your 7 out here, just let him hang out all the way to the side, and look at this set in parentheses. I see x squared as a common factor, and then what we're going to have left behind is x plus 3, and then I see that I actually am going to jump to this thought. I want x to the x plus 3 to happen over here again so that I can factor it out. So what do I have to do to make that happen? I'm going to factor out a negative 1. Negative 1 times x is negative x, and negative 1 times positive 3 gives me negative 3. I have to be a little bit forceful here, but I can make that happen. All right, so 7 is still hanging out over here. I am going to factor out that x plus 3, And what is left behind, if you let yourself see it, is x squared minus 1. All right, we take another look at this. We have a 7, an x plus 3, and an x squared minus 1. 7 and x plus 3 are very simple, but x squared minus 1 is actually a difference of squares. X squared is squared, and 1 is always squared, because you can always do 1 times 1 is 1. So let's bring this down. We won't need to keep that dot there. X plus 3, and I'm going to factor this into two binomials, x plus 1 and x minus 1. All right, if I were to use FOIL, that would go back to x squared minus 1, and look what I have. 1, 2, 3, 4 factors. That's pretty cool. All right, let's see what else we need to talk about before we're done here. Let's solve an equation by factoring. All right, if I have this, let's go back to this color. Y, this is example 4. Y equals x squared minus 9/16. We'll challenge ourselves with a little fraction. The question asks, which is a value of x when y equals 0? Okay, so instead of y, we're going to write 0. And we are going to see if we can factor this so that we can solve for the zeros. All right, so x squared is a perfect square, and believe it or not, 9/16 is a perfect square, because 9 is 3 times 3, and 16 is 4 times 4. And so the square root of 9/16 is actually 3/4. So let's write this. X plus 3/4 times x minus 3/4. I thought about the square root of 9, and I thought about the square root of 16. The top and the bottom can be thought about separately. All right, so now I know that I have x plus 3/4 equals 0, and x minus 3/4 equals 0. I'm going to solve this by subtracting 3/4. X equals a negative 3/4, and adding 3/4. X equals a positive 3/4. And so I've actually solved this, and I actually know where my two roots are, one on either side of this, like this. Let's say this is where negative 3/4 is, and this is where 3/4 is. And notice that we probably have a smile that comes down like this and goes back up like this and crosses over those x-intercepts. All right. We'll work just one example out of the homework so that you could have a chance to pause the video, or maybe two of them. Let's go ahead and do this. 5a to the third minus 20a. Pause the video, see if you can work it. Start the video back up at the point where you get stuck. All right, we're coming back, and I am going to have to factor out common factors here. I can't really go further until I do. So there's a common 5, and there's a common a. And what it leaves behind is a squared minus 4. If you use FOIL, 5a times a squared is 5a to the third, and 5a times negative 4 is negative 20a. So now I can see that I have a difference of squares, because a squared equals a times a, and 4 equals 2 times 2. So I know I'm going to factor into this pattern. I told you would have to memorize this pattern because you just have to recognize it. And once I have that, I'm actually done. 5a times a plus 2 times a minus 2 is the same thing as 5a to the third minus 20a. One is expanded and one is factored. And it's kind of funny because the, quote, expanded one is shorter than the factored one. All right, I'm going to have you work one more problem so that you can do another situation. 12a to the third plus 2a squared minus 192a minus 32. All right, pause the video, see if you can factor it. I'll give you a hint. There's got to be something common going because even number, even number, even number, even number. So there's at least a 2, right? All right, pause the video, come back as soon as you get stuck or you're done. All right, so I'm looking at this and I see that there must be a common 2. I'm going to get that out of the way here. When I take out the 2, I have 6a to the third plus a squared minus, let's see, 50 and 45 and 1. Is that 96? 192 divided by 2 leaves me 96. I did not take out any a's. And 32 divided by 2 is 16. All right, so I've taken out the common 2. I don't have any more common factors, so I am likely going to need to factor by grouping. The hint here is that we have 4 things. So we're going to put the first 2 in parentheses and the second 2 in parentheses. We're going to keep our 2 just hanging out there. It's going to be part of our final answer. We're going to look at this first set and notice that we have an a squared that we can factor out. That would leave behind a 6a plus 1. Anytime you factor out the thing, the whole thing, it leaves behind a 1. And then we want that to happen over on the other side too. So what would I need to take out to have a 6a plus 1? 96 divided by 6 is 16. And so that would be great. I could take a 16 out of both sides. I actually want the signs to change. I don't want that blue negative or that pink negative. So I'm going to factor out a negative 16, which allows me to leave behind a positive 6a and a positive 1. If I use FOIL, I can see that working. Negative 16 times 6 is negative 96. And negative 16 times 1 is negative 16. The a just goes with the negative 96 there. Let's finish this keeping the 2. I have this common factor 6a plus 1 that I can factor out. And after I factor out the 6a plus 1, what's left behind, so think of that as what goes on the outside of parentheses, is a squared minus 16. Okay, recognizing perfect squares, a squared is a times a, and 16 is 4 times 4. So I'm going to need to factor this one some more. 6a plus 1 is just fine the way it is, but a squared minus 16 is going to be a plus 4 and a minus 4. Okay, 4 is still a perfect square, but a is not. And so we are finished factoring. 1, 2, 3, 4 factors. All right, just to wrap up, I'm actually going to do one that is completely simple so that you can end with this in your mind. Let's do q squared minus 121. If I see that this is a difference of squares, I will see that this is q plus 11 and q minus 11. Q times q is q squared. Q times negative 11 is negative 11q. 11 times q is 11q, and those two cancel. And then 11 times negative 11 gives me this negative 121. Okay, hope that helps. Let me know what questions you still have.